Graph embedding learns a low-dimensional representation for nodes in a graph, such that the properties and structures of a graph are preserved by the embedded vectors. These vectors can be used for link prediction, classification, and so on. Many methods have been proposed for learning embedding vectors. Most of them adopt the following framework: determine a proximity measure and then train embedding vectors. The proximity between U and V is described by the inner product of their embedding vectors. In general, these methods are based on random walks or matrix factorization. Deep work uses truncated random walks, and Node2Vector uses a second-order random walk. Verse and APP select personalized PageRank as a proximity. Hope uses sparse SVD to decompose a matrix, such as cars and personalized PageRank. AROP preserves the polynomial proximity matrix of adjacency matrix. However, there are several fundamental problems. First, existing methods fail to preserve the out-degree distribution on directed graphs. Here shows the degree distribution of original graph and reconstructed graphs. We first observe that deep work generates identical in and out degree distributions. This because deep work trains a single embedding vector for each node, so it can only preserve structure information for undirected graphs. Verse and APP train content and context embedding vectors, but can only preserve the in-degree distribution. The reason is that proximity from U to the other nodes should be normalized. The number of pairs with large proximities is limited to a very small range, so they cannot reconstruct nodes with large out degrees. Second, many existing methods suffer from conflicting optimization goals. As we can see, PUV is 1/6 and PVU is 1. Let the inner product to approximate unequal values will hurt the quality of embedding. Finally, existing factorization methods cannot achieve scalability and non-linearity at the same time. Hope and AROP avoid n-square time complexity by decomposing a sparse matrix that's closely related to the proximity matrix without explicitly computing it, so they are linear models. However, we want to perform nonlinear operations, such as logarithm, to increase inductive strength. The key point is how to compute the matrix with time complexity of non-zero entrants instead of n-square. We propose a sparse transpose proximity embedding algorithm to solve these problems by changing the definition of PUV. The original property is the probability of a random walk from U to V, as shown by the blue and green passes in G. Consider the transpose graph. The passes from V to U correspond to the passes in G. We compute the matrix approximately with backward push. The sparsity enables to impose nonlinear functions to improve the predictive strength and to use fast factorization to effectively decompose the matrix. Thank you for your interest.